now?
Yes, sir, sure. After a short introduction of yours, we will start.
Yes, please go ahead.
So, welcome to Learning Physics with Conceptual and Problem-Based Approach, organized by National Academy of Sciences India, Nasi Delhi chapter, an 11-week course started on 27 July 2020. So we are going to be live on YouTube also, and the link will be shared with you. So today I have got the pleasure to introduce Dr. Ashok Kumar, who will be talking on thermal physics. And Dr. Ashok Kumar is Senior Associate Professor of Physics in Ramjas College, Delhi University. He did his MPhil and PhD from Delhi University in field of solar energy in collaboration with IIT Delhi. He has teaching experience of 27 years. He has taught at Eritrea Institute of Technology, Eritrea. He was also appointed as professor of physics at Addis Ababa University, Ethiopia, selected as a UGC fellow for Hungary, selected for faculty position at Zambia, and was appointed as a principal of Government College in Bihar. He has several publications in reputed refereed journals, including conference proceedings. He is also author of 4 books on optics, thermal physics, and statistical mechanics. He has been as a subject expert, resource person, and advisor at Commission for Scientific and Technical Terminology, Government of India, UGC, KBS, SSC, NU, DST, etc. So today we have pleasure of listening to uh, Dr. Ashok Kumar from Ramjas College.
Thank you, Dr. Mansi. Thank you very much. Uh, so,
So let me stop sharing my screen and you can share your screen.
so now I proceed, right, Dr. Mansi?
Yes, sir, your screen is visible and yeah,
Okay. Is it
yes,
now okay?
yeah, it is zoomed and visible properly.
The screen is totally covered, almost.
Yes, almost totally covered.
Okay, okay, fine. So now, uh, good evening, students, and very welcome to you all. This is from my side the last lecture or in thermal physics, and I was asked to cover the topics, basically the entropy and related problems, various kinds of processes in which the entropy changes, how it takes place, then different thermodynamic potentials and functions, then Maxwell's relations, the applications of Maxwell's relations, thereafter kinetic theory and molecular collisions related problems, and last but not the least, the real gas problems. So we yesterday we have completed the applications of Maxwell's relations. We have seen so many applications, and in that series, uh, we also saw that different relations also came. For example, the Clausius-Clapeyron equations and uh, energy equations, TDS equations, etc., etc. But due to paucity of time yesterday, we could not touch any problems. So let us first take some problems which would be the exemplary problem, because I believe that there is no limit of number of problems. There could be a very large number of problems, and if we solve each one by one, then it would consume the whole time. So we would not be able to cover the main subject and the very basic concept. I believe that if the concept, the basic physics and the concept is be clear, then students should be able to attempt the problems, even the unseen problems. So that is why I emphasize on the conceptual part more, and the problem is equally important. I don't say it is not important, but depending on the situation, we have to concentrate more on the concept part and give about 40% uh, emphasis on the problems. Now, the first problem, let us see, which were asked in university exam also, that prove that del u upon del p at constant v is equal to this relations. And second problem is del u upon del v at constant pressure is this relations. Now uh, these two parameters, or not parameters, but these two quantities are coming from the energy equations. If you recall, the change in internal energy with respect to pressure, the change in internal energy with respect to volume. Okay. Uh, so we have to prove it. So CV we know that is del Q upon del T. CV is actually dQ upon dt, but if that is true, it is true for partial differential also at constant volume. So dq, because the constant volume is there, therefore the pdv part is 0. dq is equal to du plus pdv. Now v is constant, therefore the pdv part is 0, and therefore whatever energy is heat energy, it is in the form of internal energy. And therefore, so this is a trick which usually the student get confused from where it came. How dq becomes d, del q becomes del u, it is because it is at constant volume. And for if we write for dq del q, then the pdv part will be 0, and therefore del q becomes del u. This can be written as del u upon del p into del p upon del t. So that these two will be cancelled out and we will have this. Now, second part. We have already defined yesterday different kind of elastic constants, and one constant was isothermal expansion coefficient or isothermal expansivity. uh, I'm sorry, isothermal compressibility. Beta is expansion coefficient or expansivity, and Kt is isothermal compressibility. So now it is the rate of change of volume per unit volume with respect to pressure at constant temperature. So this is one definition. So now, and B is, beta is 1 by V dV upon dt, which is the rate of change of volume per unit change in temperature per unit volume at constant pressure. Now from these two ABC relations can be write like this: beta upon kt is equal to 1 upon v del v upon del t p, excuse, del v upon del T at constant pressure into minus V del P upon del V at constant temperature. Now, when they cancel out, so we are left with this del P upon del T is equal to beta upon KT. Okay. Now, this sign is only the indicator of it. The parameter, they do not change. And this sign is simply the sign of increase or decrease. Therefore, we do not take it, and it is beta upon kt. Now again here, uh, dp upon, here you see that it was at constant pressure, it was at constant temperature. So we are left with only, if we take del v upon del p upon del t, it is at constant, because pressure variation and temperature variations are already there. Therefore it is at constant volume, is the d relation. Now from A, if we take, so del u upon del p at constant volume is Cv del T upon del P already done. And if we substitute these value, so then we get del U upon del P at constant volume. For this, we put the previous one, this relation, and therefore it is Cb Kt by beta. So that is how we prove it. This is one problem. Let us take another part. Is we have to prove that del U upon del V, the other energy equation at constant pressure, is Cp upon beta V minus P. Here, what we do, we know that the internal energy is function of pressure and volume if the temperature is constant. Okay, so the partial different, the perfect differential of du can be written as the partial differential in the partial differential form with two independent variables, del u upon del p at constant volume dp plus del u upon del v constant pressure dv. Okay, and also we have dq is equal to du plus pdv. So in place of this du, we write the whole equation A. So del u upon del P at constant volume dP plus del u upon del V at constant pressure dV plus PdV, this PdV. Okay. And you know that this del, if it is true for dq, it is true for del q also. So del q upon T, we divide it by T at constant pressure. So del Q upon del T at constant pressure is nothing but the Cp, specific heat at constant pressure. So here we have del V upon del T at constant pressure. We take it common out of common, and then in the bracket we have del U upon del V at constant pressure plus P. Okay, so this uh, and this del T is divided all over. So now we have Cp by beta V minus P. Cp by beta V minus P is equal to del U. This is the left quantity upon del V at constant pressure. Because this beta is defined as 1 by V del V upon del T. So del V upon del T at constant pressure left with divide of 1 by V term. So that is why the 1 by V term is put over here, and we have this relation. So this kind of problems could be asked, okay, uh, as an uh, applications of Maxwell's relation. In fact, the energy equations are applications of Maxwell's relations. So you can say it is the deductions out of the applications of Maxwell's relations. Another problem is an iron cube of side 6 centimeter is heated from 20 degrees Celsius to 300 degrees Celsius. Find out the change in work done and change in internal energy for iron if its specific heat is 0.11 calorie per gram per degree Celsius, and beta is 3.6 into 10 power minus 5 per degree Celsius. The mass of the cube is 1700 gram. Okay, so we have side this, so volume we can find out 6 into 6 into 6 centimeters. Now from the data, dq is mct formula, so therefore we put the values and we get 52360 calorie is this. In some in one book I found that it is the 52000 calorie, 52,000 calorie they have sum total they have done. And volume of the cube is 216 cubic centimeter. Now beta is 1 by V into del V by del T or delta V by delta T, rate of change of volume per unit change in temperature. So beta delta T is equal to del V upon V, or del V is equal to V beta delta del T or delta T. So it is 2.18 into 10 to power 6 meter cube. Okay, so this has been changed because from centimeter to meter, that's why minus 6 term has come. And P is 10 to the power 5 Newton per meter square. Okay, so this value uh, comes out to be delta W is P delta V or PdV, which is equal to 0.22 joule. It is slightly different from 0.22 joule. And del U is del Q minus del W. So we have 52360 into 4.2. This is the Planck constant, I'm sorry, mechanical equivalent of heat, and minus this del W term. So finally we get 219911.78 joule. So in joule unit we are giving answer. We can give answer in calorie also, but then we will have difficulty in converting other parameters because the atmospheric pressure and other things. The third problem is calculate the depression. Now this is from the Clausius-Clapeyron equation problem. What will be the depression in melting point of ice? L is equal to 80 calorie per atmosphere increase of pressure if ratio of the densities of the ice and water at 0 degrees Celsius is 10 by 11. That means the density of ice is 10, then density of water is 11. This is the ratio. Okay. Now, we know that from Clausius-Clapeyron equation that when pressure is increased, so the melting point decreases. Okay. And when pressure is increased, the boiling point increases. These two are the lower part further lowers and the upper part further up goes up. That is the effect of pressure. So from Clausius-Clapeyron equation, dP upon dt is equal to L upon T V2 minus V1. Okay. And here we have 1 atmosphere. So dP is, it is asking that per atmospheric change in pressure. In change means increase in pressure. So 1 atmosphere pressure is equal to 1.03 into 10 power 6 time. How it came? So it came from 1 atmosphere is 76 centimeter mercury column. Okay, the pressure exerted by 76 centimeter of mercury column. So 76 centimeter into this is density 13.6. Okay, gram per centimeter cube, and 980 is the G value. So if we solve it, we get 1.03 10 power 6 dynes per centimeter square. Okay, this can be converted into Newton also. Let it be dyne per centimeter square. And T2 is, because it is the melting, so T2 is 0 degrees Celsius, which is equal to in Kelvin scale 273 Kelvin. L is already given 80 calorie. So this 80 calorie is converted into joule, and this joule into smaller unit is 80 into 4.2 into 10 power 7 erg. Okay, erg is a smaller unit, joule is bigger unit of work. So at the same time, V2 by V1, we have to find out V2 by V1. So V2 by V1 is a specific volume of water. That means 1 gram water, what is the volume? 1 gram of ice, what is the volume? So it is proportional to, it is equal to density of ice, because the volume is more. That is why the volume of ice is more. That is why its density is less. So therefore it is equal to density of ice by density of water, and we have given already in the problem 10 by 11 is this ratio. But already said that V2 is 1 centimeter cube, therefore V1 is 11 by 10 into 1, that is 1.1 centimeter cube. So now we have V1, V2, and we have L, and we have dP. We have to find out dt. All right, from this relation. Okay, so now we've put the value in Clausius-Clapeyron equation. So dt is 273 into minus 0.1 into 1.013 into 10 to the power 6 divided by these quantities, which after solving we get 0.0082 Kelvin, or minus point, it is minus here also because just a mistake, I could not write here. So it is minus 0.0082 degrees Celsius. Why 0.0082 degrees Celsius? Because the measurement is in Celsius, so this will be the decrease. So we can say that with one atmospheric increase in pressure, the melting point of ice will decrease by 0.0082 per degree, sorry, degree Celsius. This is the problem and its solution. So exemplary problem of one exemplary problem from the energy equation, one from again energy equation in other words, and the third one was from the Clausius-Clapeyron equations. All these are already applications of Maxwell's relation. Okay, now so these are some examples. There are a number of examples, and I believe the one teacher has already taught you the kinetic theory. I'm sorry, the other part, so they must have covered it. So now I come to kinetic theory, molecular collision, and real gas. Yesterday, I had already said that I would suggest please come with just brushing up or reading an overall reading of the kinetic theory of gases, the molecular collisions, and real gas problem. Why? Because these are very descriptive, particularly the real gas behavior. Okay, very descriptive, and if I explain each and everything, that will consume time. Okay, so what I decided, I thought that I will explain certain things in brief, and will come directly to the conclusion. Okay, now we begin with the kinetic theory of gases. In kinetic theory of gases, you know that we have certain assumptions that all gases are made of small constituent particles. These particles could be atoms, these particles could be molecules, okay, but they are only called molecules. There is one name. This molecule is not molecules in chemistry, but the name is given as molecules. So these molecules are enormous in number. They are randomly moving in all possible directions. They never stop. Okay, they are always in motion. During this motion, they collide with each other, and when they collide, they change their direction and speed as well. That means change in velocity is also there. In this process, they collide with the wall of the container, and in this process, they impart momentum to the wall.
इसको नहीं होता क्या जूम
Pardon? Hello?
Participant,
Is it
mute
all right?
yourself.
Is it all right?
Yes, sir. Yes, sir. Please continue.
Okay. Somebody asked something, that's why I got. So in this process, they collide with the wall, they impart momentum, and you know that in imparting momentum, there is change in momentum, and rate of change of momentum is force, and force per unit area is pressure. That is why these molecules, the gas exerts pressure on the wall of the container, and this pressure is equal in all the directions because the number of molecules are enormous, okay, is very large, and the motion is so random that the average number of particles colliding in all the walls are almost equal. Therefore, pressure in all the directions are equal. Now, we are not going in detail how we derive and how we reach uh, up to the final expression. The final expression for pressure exerted by an ideal gas or perfect gas. Ideal and perfect gas means the energy There is no intermolecular attraction. There is, because we assume the mass of the particles or mass of the molecule is negligible. At the same time, the size, important thing is the size of the molecules are negligible compared to the volume of the gas, right? And at the same time they do not, because the mass is negligible, so intermolecular attraction or interatomic attraction is negligible. So whatever energy they have, there is no potential energy, the energy is only in the kinetic form. Okay, so these two are basic assumptions of a perfect gas, and that is why they are called ideal gas. However, we know that such ideal gases are not practically found, and all the gases are real gases that we will discuss later on. Okay, so pressure exerted by an ideal or perfect gas is m, where m is mass of the molecules, n is its density, that means molecular density, or the number of particles in unit volume, and C square is root mean square velocity. C is root mean square velocity, and V is the volume. So this comes out to be this number of molecules, and this is mass. So m into n is the mass of taken of the gas taken in the container upon 3 V and C square. This C is called root mean square velocity. What is this root mean square velocity? That we have to check it. Okay, so again, very fast, we know that suppose we take one molecule. So this molecule has in one direction, we, for simplicity, we solve it like that. The three perpendicular directions are along x, y, and z axis. And suppose the velocity of particle number one, this one means any arbitrary one selected one, is along x-axis it is u, along y-axis it is v, and along z-axis let it be omega. Okay, so we can say that the c1, that is the velocity of net velocity of first particle, is, this is actually the resultant velocity. Okay, so mid of the composition of these three velocities, and because velocity is a vector quantity, therefore three velocities acting on this particle, their composition result into C. So C1 square can be given as U1 square plus V1 square plus omega 1 square. Similarly, for another particle, particle number 2, C2 square can be written as U2 square plus V2 square plus omega 2 square, and so on. Okay, so if n number of particles are there, so C can be written as the C1 square plus C2 square plus C3 square plus Cn square divided by n number of particles. This whole term is called, it is the mean of, it is the root of the mean of squares of velocities of particles. Is it clear? It is the root of mean of squares of particles of the molecules. Okay, that is why its name is CRMS, or root mean square velocity. Now, this P can be written as, if we take m upon v as rho, so 1 by 3 rho c square. Therefore, c square is equal to 3p upon rho. Now, this is a very observable quantity. That means rho is density of the gas and p is the pressure of the gas. So by just measuring the density of the gas and pressure of the gas, we can have an idea of the root mean square velocity of particular gas. Okay, so now the order of such, just an idea of order of C, that means root mean square velocity for hydrogen, it is 18.4. If we put all the values, 18.4 into 10 power 4 centimeter per second. For oxygen, it is 4.6 into 10 power 4 second centimeter per second. and for carbon dioxide it is 3.95, that is 4 into 10 to the power 4 centimeter per second. Now here you see that the density is less for hydrogen because it is only the hydrogen is a diatomic molecule, and the atomic mass is very less, or molecular weight is very less. Therefore, we find that the molecular speed, that is root mean square speed, is very high. Okay, so and as the molecular weight increases, it also increases. So uh, so this is the reason. Now from here, the kinetic interpretation of temperature. Now these are the formulae which are given. Numbers are important in the sense that numerical problem, brief numerical problem could be asked with the help of to solve with the help of these formulae. Now, kinetic interpretation of temperature. So, half mc square is equal to 3 by 2 kT. Now, from where it came 3 by 2 kT? Because we know that the kinetic energy, here you see we have unique thing, half mc square. This is a parameter, this is kinetic energy, but in this kinetic energy, m mass of the molecule and c is the RMS value, okay, of the molecule. This is microscopic description. You don't know the velocity of one molecule, and that too the RMS velocity. But here you see 3 by 2 K is Boltzmann constant. Okay, somewhere in some book it is written KB also. Doesn't matter, it is the same, K or KB. And T is absolute temperature. So here you see that this is observable. Only one T is you need to observe or measure. So this microscopic parameter connected with the macroscopic observable is. So from this relation we find that because m is constant, k is also constant. So we can say m is constant for particular gas, right? So c square is proportional to t, or c is root under t. So we can say that the temperature is the root of the temperature is nothing but the average kinetic energy, or the depends on the square of the root mean square velocity of the molecules. Okay, so from this relation we can have some problems, problem on based on these relations. So now if we solve it, okay, we solve it. Now here uh, C is proportional. This is equal here written because the constant term have been taken care of. So it is, that's why it is proportional. You can also say, or you can say equal, doesn't matter. So now these relations do come not from the simple kinetic theory, but we have to depend on the Maxwell's distribution of velocity, in which we statistically approach for the measurement of the number of molecules having particular value of velocity. Okay, and there, because that I cannot explain here in detail. Okay, so on that basis we find the RMS value CRMS is equal to 3 kT upon m root under.
सोच रहे थे आपके
Yes.
होली ये होली के बाद
Now,
Yes, please mute yourself, participants.
yes, some signals are coming. Students are requested, suggested. Okay. So now the average velocity, what is this average velocity? Average velocity, RMS velocity, and most probable velocity. These three are different. The RMS velocity is found out by the expression already given earlier. Excuse me. Already given earlier. The average velocity is simply the mean of the velocities of different molecules. All right. So if V1, V2, V3, V4, V5, etc. are there, divided by n number of molecules, this is average velocity. Of course, here to we use C value. Okay. So, but it is the velocity. Some books use V RMS, V average also. And most probable velocity is that velocity which is being acquired by most of the molecules. Now, these three things are different. All the three need not to be equal. They are different. RMS velocity is the root of the squares or root of the mean of the squares of the velocities. Average velocity is the average of different velocities, simple average, okay, or the mean. And most probable velocity is, suppose some velocity is v1 acquired by, suppose, n1 number of molecules, v2 by n2 number of molecules, because one velocity will maybe for others molecules also. Okay, so the molecules will be the velocity will be distributed among the number of molecules. Okay, but we find that there are certain velocity, certain value of velocity which is very commonly found, that is called most probable velocity. This can be illustrated as this. I illustrate it with one example. Suppose in a class, suppose in your class, the students are of BSc final year, right? Or first year, let us say. If we take the if we take the age of the student, so average age could be that age of suppose 60 students, so it could be you add the age of some students 20 years, some is 19 years, some is 18.5 years, and so on. You add all and take the mean, so that would be average age. But what is the most probable age? The most probable age is you find the frequency that 18.5 years or 19 years or 20 years, how many students have the same age. Okay, you will find that there is a particular age which is being shared, or that age is common to maximum number of students. Okay, the same number will be different for different class because the age has changed. All right, particular class, it is possible that some students are very young. Okay, in very early age they started studying, and even the 17 years old student is in graduation. But at the same time, some one student who started late could be in 23 years. Okay, but the majority will be in 20 years range. So that is called most probable velocity. So most probable velocity, the value need not to be maximum, but this value is attained by maximum number of molecules. That is the meaning. Okay, so if we take the ratio of these cm is to c average is to c rms, we have this, and we find this 1 is to 1.128 is to 1.225. So you see that it is gradually increasing. Okay, but of course the difference is not much. They are very close to each other. All are 1 point something. Okay, so if we plot the graph, what the plot the graph? We plot the graph of dn upon dc. What is this? This is actually the distribution. What is the meaning of distribution? Number of molecules per unit number, not per unit, in particular range of the velocity. If, and here is the velocity, we find that this is increasing gradually, attains a maximum, and gradually it decreases. The rise and fall both are exponential in nature. Okay, both are exponential in nature, and this distribution is called Gaussian distribution. What is the meaning of it? That means if we select particular value of velocity, that means the velocity value is very less. For example, just an example, 1 meter per second. Okay, so we find that the number of such molecules having velocity 1 meter per second is very less. If we increase the velocity 2 meter per second, then the number will increase. 3 meter per second, number will increase. 4 meter per second, further increase, and so on. We attain a certain maximum. Okay, and thereafter if we further increase the velocity, suppose 25 meter per second, then we find that again the number is decreasing. That means there is a particular value of velocity which is being acquired by maximum number of molecules. This particular value is called maximum probable velocity. But don't get confused here. You find that the maximum probable velocity has the value, because x, along x-axis the c is, the velocity is increasing. Therefore, RMS value is greater compared to this, The value itself is minimum among these with the most probable, but their numbers are maximum, which is this, followed by average velocity and root mean square velocity. So this is the Gaussian distribution gives a lot of information, and very interestingly, this Gaussian distribution is a kind of distribution which we find in majority of the phenomena and majority of the thing in the universe and in our day-to-day life. Okay, how? If you find that number of persons extremely poor in society, that is also very less. And if you find extremely high, that is also less. The majority of the people fall in this range. Okay, so in making the statistical planning, so this statistical data become very useful, and this curve may have different slope for different properties and different nature, but it is of great importance. Now we leave at this stage. In regular class it is possible to explain further all this. So now we come to, in the molecular collision, kinetic theory and molecular collision, the next thing is degree of freedom. What is degree of freedom? We know that the molecules are free to move in all directions, and we have also seen that the energy is associated with this movement, because all the energies are kinetic in nature. But we know that the molecules have not only rectilinear motion or translational motion. The molecules can have translational motion, that means the motion which can be, for simplicity, assumed as along XYZ direction. Try to understand, it is hardly possible that the molecules are moving along XYZ direction. Never. It is moving along any arbitrary direction. It can move along, suppose the molecule is moving like this. From here, there is one straight line. That's all. Its direction is in 3 dimension along any one direction. But one thing, whatever be the direction, you can resolve this velocity along 3 perpendicular direction, and that resolution, suppose this is c1, so this can be resolved in along x-axis u1, along y-axis v1, and along z-axis. Z-axis is beyond the paper or beyond the board or beyond the screen, so it is z-axis, so omega 1. All right, so this is the situation. Okay, so this is similarly for second molecule, etc. So this is all about the translational or rectilinear motion. But at the same time, the molecules can have rotation also. The molecule can rotate along certain axes. So it is said that what is degree of freedom? So degree of freedom, so if suppose you have to find out the energy of a particle for simplicity. Okay, so you know that from kinetic theory basis, whatever energy of the particle would be, it would be just what? Half mv square, nothing else. Half mv square. Because we have already assumed that it does not have any potential energy, so kinetic energy. Now, if you know that the particle is free to move in this direction, and the velocity you know, what you will do? Half m into the velocity square. Simple. You give the answer. And you don't know the other two velocities, but if you know the other two velocities, then also you will include those velocities, and finally the total energy you will calculate. That means that depending on the directions of movement of, or the possible directions of movement of the particle, you are being able to describe about the information related to its energy or position of the particle, right? This direction, the information of directions, are called indirectly degree of freedom. Degree of freedom in the sense that what are the degrees in which the particle is free to move. So it is the number of independent variables. Here it is variable. It is variable. Why? Because this is generalized case. In this particular case, the particle is free to move. All right, but not only movement. If we have to describe its position, then also if it is here, so here, from here to here, the distance from the x-axis is the same. So this is incomplete information. The complete information will be when its x and y coordinate is given, and even then more complete information when the x y z coordinates are given, right? So the position is also incomplete unless until you describe the three independent variables x y z. Similarly, the information related to energy or kinetic energy is only possible when you describe Vx, Vy, Vz, right? So these variables are called degree of freedom. So I have written it is the number of independent variables that must be known to describe the state or the position of the body completely. State does not mean physical state. State means energy. State means energy state, and position means position state. Position state means potential energy. This is kinetic energy. So full information is required. It can be given only when the complete number of variables are given. Okay. So this is what. So if, for example, if there is a ball and this ball is contained, this ball is contained in a hollow tube. Hollow tube means like a small pipe. Okay. So ball is free to move only along one direction, that is the direction of the tube. So we say the degree of freedom is 1. Now, suppose there is an ant, okay, and this ant is moving on the table and cannot fly generally, okay. So we say that the ant has degree of freedom 2 because it has x and y directions freedom, so it can move in a surface. So degree of freedom becomes 2. If there is a fly, so it can move along x y z direction in the space, so we say it has degree of freedom 3. But if the fly can rotate also, okay, so degree of freedom will increase, so 3 and plus rotation. Now how this can rotate, that we will explain later on. But before that, there is a law, and that law is called law of equipartition of energy. I have not written, please note down that the law of equipartition of energy says that the energy, total energy of the system is equally distributed among the different degree of freedom of the particles, and with each degree of freedom, the energy, average kinetic energy is equal to half kT. Two things. Number one, that whatever energy is, this energy, say for simplicity, for one molecule. So energy of the one molecule or energy of a system is equally distributed among all the degrees of freedom. If the particle has only 1 degree of freedom, then the total energy is equal to 1 degree of freedom. Okay. If it is 2, then it will be equally distributed. If it is 3, so the total energy is equally distributed among each degree of freedom. Okay. And for each degree of freedom, the value is half kT. So for a molecule which has in general 3 degree of freedom, right, x, y, z direction, so what should be in total energy? It should be 3 by 2 kT, and that is what I had written earlier at one place. This, you see, half mc square is equal to, because this c is composed of u, v and omega, if you recall. So u, v and omega was nothing but along x, y, z directions. So it is 3 by 2 kT, half kT, half kT and half kT. Is it clear now? Students, are you getting? Am I in good pace?
Yes, sir.
Okay, okay, fine. So now, uh, for, all right, all right. Because I should take feedback from a student, whether I am slow or fast. So now, uh, so the general rule is the total energy is equally distributed among all possible degrees of freedom, and for each degree of freedom, the energy is half kT. All right. The earlier one was just an illustration. So now take the case of monoatomic gas. Monoatomic gas means a gas which has one atom. For example, helium, argon, etc. Okay. So it is atomic gas. Okay. But the atom itself is called molecule in kinetic theory, that you don't get confused. Okay. So degree of freedom is 3. Now why degree of freedom is 3? Because it can move along 3 perpendicular directions. But the molecule can move, can rotate along its axis. Then why not taking along the axis? Now you see, if it is a molecule, we assume that it is a compact structure. The molecule is spherical in nature. Okay. And where is the center? So center is passing through its center. Okay. So if it is rotating for a sphere, so any diameter could be the axis of rotation. All right. But at the same time, the total mass can be assumed to be concentrated at the center of the molecule. All right. When it is at the center, the axis will also pass through the center. So kinetic energy of a rotational body is half I omega square. Is it all right? What is I? I is equal to moment of inertia. Okay. Hello. What is moment of inertia? Moment of inertia is mr square. Okay. So now r is 0 here. So automatically r is 0 because the distance from the axis of rotation to the point of rotation. So this distance becomes 0 because the axis passes through the mass itself. Therefore, the moment of inertia value is 0. Therefore, rotational kinetic energy term is 0. And whatever energy is, it is only translational or rectilinear, and therefore degree of freedom is only 3. All right. If it is diatomic gas, then diatomic gas, I did not put the diagram here. I should have put here that if it is diatomic gas, so the whole system, diatomic means suppose one atom is here and one atom is, two atoms are joined making a molecule, and they are connected in between. So now the whole system, and it has one center of mass somewhere. This whole system is moving along x direction, y direction, and z direction. So 3 degree of freedom, translational. But at the same time, this molecule can have rotation. Now, if the axis of rotation, suppose one molecule is here and another molecule is here, please see the cursor, try to visualize it in your mind. One more atom is here, one atom is here, and axis of rotation is passing through the center. And if it is rotating clockwise or anti-clockwise, then one motion is along this, right? Suppose it is anti-clockwise, so it is along the axis which is vertical in nature. Is it all right? So one more degree of freedom. Another degree of freedom is that one atom is here, one atom is here, and the line joining is this, and the axis is passing through the center, but it is perpendicular to the screen. Is it all right? That means it is perpendicular to the screen. That means if you see from here, you will see only a spot, not the axis. Okay, this is just like this. This is just like this. So now it is moving like this. The molecule, the atoms are moving like this. The atoms are moving like this. Okay, earlier it was going inside the screen, coming out and inside the screen. Now here it is not going inside the screen. It is on the surface of the screen and it is rotating like that. So 2 degree of freedom. Think about the 3rd degree of freedom. The 3rd degree of freedom is the axis is passing through the line joining the 2 atoms itself. That means it is parallel to the plane of the screen. All right. Now in this case, the rotation would be along this axis, but here in this case what we find that the distance of the mass from the axis of rotation is again 0. Why? Because the axis of rotation is passing through the center of mass. Therefore, the moment of inertia along this axis becomes 0. So this is not of interest. So finally, we have only 2 degrees of freedom due to rotational motion and 3 degrees of freedom due to translational motion, total 5 degrees of freedom. All right. In case of tri or polyatomic gases, we can have 6 degrees of freedom or 7 degrees of freedom. Now question is how 6 and 7, that also you understand. Now in this case, we have one atom here, another atom here, and another atom. But this is only possible when the 3 atoms are at 3 different places. The molecular structure could be like this, but the molecular structure could be like this also, in one line. Now, if the 2 molecules are such that they are equal, or all the molecules are equal, then, however, it is not generally possible. The 2 atoms are equal, one atom is different. So in such case, the moment of inertia along the 3rd axis, which we assumed here parallel to the plane of screen, that is not negligible. That has finite value of moment of inertia, therefore energy also, and we have 6 degrees of freedom. But at the same time, it is possible that the degree of they are not of the same mass, and at the same time the axis is not passing through the center, exact center. It is different. Okay, it is possible that the axis of rotation is not symmetric to all the molecules. It is possible. So in such case, the degree of freedom becomes 1 more, 7. So whatever be the situation, so in general we have 3, 5, and 6 degrees of freedom for a molecule, and depending on that, we find that we have different values of energy. associated with the molecules. Now, this law of equipartition of energy and concept of degree of freedom is of great use in uh, classical thermodynamics or classical statistical mechanics, in the sense that you can first find out the atomicity of the gas, whether the gas is monoatomic, diatomic, or polyatomic, or triatomic, or we can find out the specific heat value of the gases. We have theoretical value as well as experimental value. Let us see how we proceed. Let us see here. Now, energy with each degree of freedom is half kT. So, energy with 3 degree of freedom, we are discussing about the monoatomic gas. We will try to find out the specific heat. Now, specific heat means specific heat at constant volume, specific heat at constant pressure, and from there we can find out the ratio of the specific heats also, that is the gamma value. So 3 degree of freedom, 3 into half kT is equal to 3 by 2 kT. Now, for 1 gram mole of the gas, okay, in many books you find it is written GM. This is wrong. It should be G only. 1 gram. For gram, the notation is standardized as G, not GM. Either you write gram, GRAM, or you write G. Okay, just for your information. Of course, marks is not going to be deducted. Mole of the gas. So energy associated is 1 gram mole will have how many molecules? N number of molecules. Is it clear? Any problem? What is N? N is Avogadro number. In some books and some places we use A also. What is N? Avogadro number. This is always constant. Whatsoever you take the material, oxygen, hydrogen, nitrogen, carbon, methane, anything, if you take 1 gram mole, the number of molecules contained in 1 gram mole will be the same. All right, the number will be same, and this number is Avogadro number. Why it is same? You think over it. Okay, if I explain, it will take time. Because the heavier the molecules, okay, the heavier the molecules, the heavy will be, the greater will be the molecular weight. So automatically in gram mole you will take large amount of material, so number of molecules will come the same. If it is lighter, so hydrogen 1 gram mole is only 2, so therefore the number of molecules will be the same. If you take 2 gram mole of hydrogen, automatically the number will be the same Avogadro number. So this is the beauty, and this is equal to 3 by 2 nkt, and 3 by 2 nkt, nk is equal to RT, okay, from PV. So this is 3 by 2 RT, okay. See, the energy is 3 by 2 RT. Here, try to understand, this is internal energy. And the internal, whatever internal energy, it is the energy due to heat. It is the internal energy due to heat energy, and that energy is the due to molecular motion, energy contained by the molecules. So it is 3 by 2 RT. Now we define for an ideal gas, because the gas is ideal, so whatever energy is, that is only the function of temperature. We assume it will not be function of other parameters like potential energy. So function of temperature means totally kinetic energy. So can we write Cv is equal to du upon dt, okay, and this is equal to 3 by 2 into R. This T is gone. So now in this situation, but at the same time Cp minus Cv is equal to R. So Cp can be written as R plus Cv. So in place of Cv we write 3 by 2 R and plus this R. यहाँ उल्टा हो गया. So this is equal to 5 by 2R. All right. Now for monoatomic gas, can we write gamma is equal to Cp upon Cv is equal to 5 by 2R divided by 3 by 2R. Okay. So finally we have 5 by 3 is R cancels out and it is 1.67. So now 1.67 value theoretically we calculated based on the law of equipartition of energy and the concept of degree of freedom. This is the theoretical value. Now we will discuss later on the experimental part. Similarly, if we take the case of diatomic, so degree of freedom becomes 5. In the same manner, we will proceed and we will find that I'm not going to just invest time here. Okay, Cp is comes out to be 7 by 2R. So Cp by Cv is equal to gamma is equal to 7 by 5. 7 by 2R by 5 by 2R is equal to 1.40. This is the case for hydrogen, oxygen, nitrogen, common diatomic gases. Here, common inert gases. Okay. For triatomic, we have degree of freedom 6, so gamma comes out to be 4 by 3 and it is 1.33. If it is 7, rare case, gamma comes out to be 9 by 7 is equal to 1.28. Now, interesting thing is that the value it's theoretically calculated for gamma for monoatomic, diatomic, and triatomic gases are very close and in very good agreement with the experimental value, because there is a Dulong method of calorimetry by which the gamma value is measured. Long back earlier in MSc, this experiment was there to find out the value of a specific heat ratio for monoatomic, diatomic gases. So now it is not there. So in this case, we found that the experimental value is very close to the theoretical value 1.67, 1.4, and 1.3. It is decreasing. Okay, with atomicity, with increase in atomicity, there is decrease in the gamma value. Okay, so this could also be a question objective that the with increase in atomicity, the ratio of the specific heats gradually decreases, increases, remain unchanged. It has no business like that. So this question conceptual could be asked. Okay. So now we come to again kinetic aspect. In kinetic aspect, this is all about the classical. So we can say that the theoretical basis which we assume has is correct to great extent. Of course, this law of equipartition of energy and this the concept of degree of freedom deviates in the range when it is applicable to very high temperature and at very high temperature. Now, why it happens when the temperature is very high, not only the translational and rotational motion come into existence, but the vibrational motion of the molecule also contribute. And we know that the vibrational motion also has energy, associated energy. So that we have neglected, and therefore there we find that there is deviation in high range of temperature. So that need to be taken care of. So that we do later on. Okay. So now we come to mean free path. What is mean free path? So first of all, what is free path? We know that from kinetic theory, we know that the molecules are randomly always in motion. What is the meaning of randomness? What is the meaning of randomness? Any student? Any student, if you respond, what is meaning of randomness? Are you getting me? No one is responding. Uh, Randomness
Please
is
write answer in the chat box.
Yeah, I have gone, but I am not getting any answer. Anyway, so doesn't matter. Okay, never mind. So randomness is actually which cannot be predicted. That is meaning. Randomness means which cannot be without foundation movement. Yes, it is not only movement, but it is in all sense which cannot be predicted. Pre-prediction is not possible. Okay, so it can, this is just like that, a drunken person, a heavily drunken person, what will be his next step is very difficult to predict. Yeah, he is moving forward and immediately he will, the next step will be backward. So we say that he is randomly moving. Okay, so that means the molecules, you cannot predict what will be the next step or what will be the next direction of the molecule, because in the number is so large inside the chamber, okay, or in the container, that every time they are colliding with each other, and the next direction is unpredictable, and therefore they are moving, they are said to be in random motion. Okay, that is the meaning. So in this random motion, they collide with each other and they change their velocity, in the sense that they change their direction of the speed and the magnitude of the speed both. Okay, so, and how, when they collide, they may collide after a very long time. That means they traveled for without collision for a quite long distance, but it is possible that next time it will collide immediately. So the distance traveled between two consecutive collision is called free path. It is the free path. During that distance there is no collision. Okay, so let it be it is denoted by lambda. So lambda 1, lambda 2, lambda 3, etc. are up to lambda n. It is simply a number. Suppose it is 10. So for 10 consecutive collisions we have 9 distances. Okay, and these distances are lambda 1, lambda 2, etc. So if we take, so lambda 1 is one free path, lambda 2 is another free path, lambda 3 is another free path, and so on, so forth, and n is the number of such collision, then we can say that the average of these free path is mean free path. So we say that the mean free path is the mean of the free paths traveled in n number of collisions. Okay, so this is, so what, how we find out? So we find out it as the total distance, the average velocity of the molecule, and in fact it is total distance traveled divided by total number of collisions. In other words, the time taken in n number of collisions and the average speed of the molecules during that duration, and divided by the number of collisions. So that is the concept of mean free path. Okay, so this mean free path is that the when the molecule will collide with each other. Suppose there is one molecule, this one, another molecule is this one. So the collision is only possible when the molecules, they touch each other, the boundary, they touch each others. Okay, and if radius of the molecule be sigma, radius is denoted by sigma. So I'm sorry, uh, radius is sigma by 2, diameter is sigma. Okay, diameter of the molecule be sigma, so radius is sigma by 2. So when they will touching each other, so distance between the two centers of the molecule would be sigma by 2 plus sigma by 2 is equal to sigma. Is it clear? Okay, so now we imagine that there is a sphere whose radius is sigma. Imagine there is a sphere whose radius is sigma. So any molecule which is coming within this radius will collide. If it is beyond this radius, or it without, I'm sorry, with which is beyond this sphere, is not going to collide with this molecule. So for collision, it is necessary that the other molecule should come in the range of this sphere. This sphere is called sphere of influence. Okay, so we can say that the condition for collision is that the molecule should come in the sphere of influence of one molecule. So this is case with each and every molecule. Okay, and with some we imagine that for in t time the distance traveled is v. Okay, distance traveled, because v is the velocity in unit time. So in there is a cylindrical structure formed out of it, and all molecules coming within this cylinder will be in that time will be in collision. So finally we get, as a result, we cannot derive the expression over here, and finally we get the expression for excuse me, lambda, that is the mean free path, is equal to 1 upon pi sigma square into n. Okay, it is in denominator. Sigma is the diameter of the excuse me, diameter of the molecule. Now it was found that this relation is not very correct. There was some correction needed. I am not going in detail to explain all this. And finally, the correct formula was given by Maxwell, and it says that the correct formula, the correction term, is this 1 by root 2 pi sigma square n. Only 1 by root 2 was introduced, and which is equal to m upon root 2 pi sigma square rho. Now this is very good. N is equal to rho upon m. Rho is density. So density, because it is molecular density, so density upon m gives the number. Therefore, it has been replaced by this. Okay. So these are measurable parameters. Okay, and sigma is the size. So the size is also a big determining factor in mean free path. So greater the size, naturally the chance of collision will be more, and therefore the free space, that means the less collision state, will be less, and therefore mean free path will be less. So this is the concept of mean free path. So order of mean free path is this. Order means just an idea what is practically the mean free path value. So for hydrogen, it is 1.83 into 10 to the power minus 5 centimeter. It is at NTP, because you see NTP or STP, that means normal temperature and pressure, 0 degrees Celsius and 1 atmosphere. For nitrogen, it is less, 0.94 into 10 to the power 5. For oxygen, it is 0.99. So we can say that with increase in molecular weight, because nitrogen is heavier in the sense, 17 is this, and it is 16 only. So therefore, we find that with greater the molecular weight, okay, the mean free path decreases gradually. Effect of temperature and pressure on mean free path. So the formula is given by lambda is equal to kT upon the same, okay, root under 2 pi sigma squared by p. That means lambda is directly proportional to t, and lambda is inversely proportional to p. That means if you increase the temperature, the mean free path increases. And if you increase, this temperature is absolute temperature, and if the pressure is increased, the mean free path decreases. This is very natural, because when temperature increases, the average kinetic energy increases. Now, with this increase in average kinetic energy, what happens? The velocity increases. Okay, so greater distance is traveled. So of course the collision will increase, but the particle will be more in random motion. So in totality, more distance will be covered because average distance traveled during the n number of collisions. That was the definition. Therefore, greater distance is traveled because of the v value increased, and therefore lambda increases. And p is inverse, p has inverse effect, meaning by if you increase the pressure, the volume will decrease and the gas molecules will come closer to each other. So freedom will be seized and therefore lambda will be less. So some numerical problem could be asked based on this only. Okay, or not, no, I'm sorry, not numerical problem, rather some conceptual problem could be asked on this. Now come to the transport phenomena, which is again based on the collision of molecules. Okay, that was also collision of molecules. Here transport phenomena. Why we call them transport phenomena? Very short. I am trying to brush up the whole thing which you have read earlier. Okay, but I emphasize on the very conceptual aspect on which the problem could the question could be asked. Not only problem based but theoretically also. Excuse me. Any physical process which is caused due to transfer of certain quantities are called transport, because the cause of the physical process is because of transfer or transportation of certain physical quantity. So now, first we know that in kinetic, on the basis of kinetic theory, the molecules are randomly in motion. So what happens? Due to the motion, they transfer momentum. When they are in motion, they transfer, there is kinetic energy. So when they collide, there is transfer of kinetic energy also. The kinetic energy is in the form of temperature, that is heat energy. So we can say that energy is also transferred, momentum is also transferred. And in this process, the molecule themselves also transferred from one place to another place. Depending on these three situations, we have three physical phenomena. Number one is viscosity. So viscosity is, you know, viscosity you have read in schools also. It is the property of fluid, not liquid or gas. It is property of fluid in which there is relative motion between the two layers, and the motion is such that the each layer tries to retard the other layer. Okay, so you can imagine that the gas is randomly moving, and we can understand that there is a flow of gas or flow of liquid. Liquid can be understood in a better way. So what happens? The layer of the layer which is, imagine a one molecule, one set, a layer of single molecule thickness, right? A layer of single molecule thickness. So which is in contact with the container, which is in contact with the tube or the surface. So what will happen? Those molecules will be in static situation, that will be in rest, we can assume. Okay, and as we go up, so molecule will be in greater motion. Okay, so velocity, so those molecules, imagine another layer above it has greater velocity, above which again greater velocity, above which again greater velocity. So we can say that there is a velocity gradient as we go from below to upside. All right, if it is tubular structure, so we can say that the molecules of water in the vicinity or in the circumference which are in touch with the tube are at rest, and as we approach towards the center, radially towards the center, the velocity increases. At the center, the velocity is maximum. But as we cross the center, go other side, the velocity again decreases. So we can say that there is velocity gradient of the molecules of water or fluid as we go from the circumference to the center side. Is it clear? Okay. So now these molecules are in motion. So what happens? The lower molecule are at rest and the upper molecules are in motion. Due to inertia, the upper molecules will try to drag the lower molecules. They will try to pull the lower molecules, and the lower molecules will try to pull backward the upper molecule. Is it clear? Okay. So the upper molecule will be are in greater motion. Lower molecules are also in great motion, but in less motion. So meaning by there will be the velocity difference, and due to that, what will happen? There will be a velocity gradient. Now the question is how these two molecules will collide, how these two layers will transfer, will interact. It is only possible when some molecules from the lower side will go up side and some molecule from upside will go to lower side and they will interact, they will collide because it is gaseous medium, it is fluid medium. So this interactions of molecule will transfer the momentum exactly in the same way as it was doing inside the container while deriving the pressure exerted by a gas, right? So there, for simplicity, we took that it is a straight line going, colliding with the wall. The momentum is mv. Okay, the after collision, the momentum is minus mv because it is elastic collision. There is no loss of energy, no loss of uh, velocity, and therefore minus mv, changing momentum mv minus mv is equal to 2mv. Okay, and then you found out the rate of change of momentum and finally the force and pressure, right? So similar situation is here, and I'm not going to do the mathematical jugglery in between. So finally what we get, that we find the coefficient of viscosity, and which is in brief the Poiseuille's formula as we derive the coefficient of viscosity denoted by eta is equal to 1 by 3 rho v average, okay, average velocity lambda. This lambda is this mean free path, because this is very important, because it depends that what is the mean free path. Okay, so if mean free path is more, the viscosity will be more mean free. That means this is the distance by which there is collision. So if suppose we imagine that one layer is here and other layer is here, and mean free path is lambda. So suppose the distance between the two layers is 2 centimeter and mean free path is 1 centimeter. So under no circumstance the molecule will go to collide with other molecule. Impossible. Okay, in general, because mean free path is this. So it is necessary that for collision, the distance between the two layers must be less than equal to lambda mean free path. Okay, that is the condition. So if we put the value, finally we solve it as 1 by root 2 pi n sigma square mv average by 3 root 2 pi sigma. So this is just an information. Finally we get this value. Okay, you need not to just mug up, keep it in mind. Okay. Now other one is thermal conductivity. What is thermal conductivity? So first of all, conductivity, the mode by which the heat is transferred or energy is transferred from one molecule to another molecule. Now you know that the thermal conductivity is basically due to vibration of molecules. Okay, so in case of solid it is vibration, but in case of gas and liquid it is basically the molecule go from that place and impart energy. Okay, so the here in this case, as we took consideration of momentum, here we take consideration of temperature. Okay, so molecules which are at the bottom are at higher temperature, we imagine, because conduction is will take place only from higher temperature to lower temperature side automatically without any external force, right? So condition of temperature difference is very important. Okay, so now imagine the lower layer is at higher temperature, upper layer is at lower temperature. So when we go from bottom to up side, in earlier case there was increase in velocity. Here we have different situation. As we go from bottom to upside, there is decrease in temperature, right? Because the lowest one is the highest temperature. As we go up, the temperature gradually decreases. So we can say that if the T is the bottom temperature, so at certain distance, the temperature is reduced by dt. So T minus dt is there, and so on. All right. So now in this case also what will happen? The molecule will be transferred. The hot molecule will come on lower side. I'm sorry. Cold molecule will come on lower side and hot molecule will go on upper side. Okay. And in this transfer there will be transportation of energy, and due to which the heat will be conducted. Now, the thermal conductivity, we know that this thermal conductivity is equal to, as we have read in the schools, is equal to the amount of heat transferred from the hot side to cold side at a temperature difference of 1 degree Celsius across an area of 1 meter square when the two surfaces are at a distance of 1 meter. That is ideal. In 1 second, time is also there. So what are the condition? The temperature difference should be 1 degree Kelvin or Celsius. The surface area should be 1 meter square. The distance between the two layers should be 1 meter, and time should be 1 second. All right. So the amount of heat becomes K is given by Q is given by K A theta 2 minus theta 1 into T divided by D. That was the formula, if you recall. So D is the distance between the two ends and T is the time. Okay, theta 1, theta 2 are the two temperatures, and K is a constant of proportionality, which is called coefficient of thermal conduction or thermal conductivity. So metal has better K, and poor conductors like wood and other things have poor conductor. You do experiments also for good and bad conductors, right? So thermal conductivity, finally we derive the expression 1 by 3 rho V CV, specific heat, lambda, and up to here we have, up to except CV, up to here we have it is eta. So we can say eta into CV is nothing but thermal conductivity. So very unique. The viscosity is mechanical property we had idea so far, and thermal conductivity thermal property. So now from kinetic point of view, you see this mechanical property and thermal conductivity, the property, they become equal just by one term. Okay, so in kinetic view, these all properties are the same. All right. Now the third one is diffusion. In diffusion, what happens? The higher concentration and lower concentration, if two gases are there, either same kind of gas or two different kinds of gas. For simple case, we take same kind of gas, okay, but they are at different concentration. So due to the pressure of the gas, there is movement of molecules from higher concentration to lower concentration site, and from lower concentration to higher concentration site. uh, no, I'm sorry. The molecules do not move from lower concentration to higher concentration side. So there is movement of the number of molecules from higher concentration to lower concentration side more. And when there is this process continues till equilibrium is attained, And this coefficient of diffusion or diffusivity is decided by the expression sigma upon, I'm sorry, eta upon rho. That means the viscosity and rho is density. So lighter the gas, more will be diffusion coefficient. That means more quickly diffusion will take place. They will be homogeneous more quickly. And as lambda is proportional to T by P, and also the V is root under T. This is nothing but the same C. Okay. So there it was root mean square velocity, but it is velocity. So velocity, average velocity is root under root T. So we can say that the diffusion coefficient is T upon P root under T, and finally it is D proportional to T root under raised to the power 1 and T raised to the power 3 by 2. Meaning by if we increase the temperature, more effect will be on the diffusion than the pressure. So objective question could be asked that the diffusion of two gases will more depend on pressure, less on temperature, more on temperature, less on pressure, and so on and so forth, like that. So these minute things you have to keep in mind so that you can solve such problems. Now we come to the kinetic theory and molecular motion. These two aspects are over. Now we come to real gas. We have very less time. Now, real gases are the gases which we deal with. Okay, so all gases are real gases, and real gases are not ideal gases. Why? Because in ideal gas or perfect gas, we assume PV is equal to RT, or PV is equal to constant, or PV gamma is equal to constant for different conditions are true under a situation when the gases are considered as the same, satisfying the same conditions as given by the hypothesis or assumption in kinetic theory. Assumptions I am not going to repeat. The molecules are very minute in size, their masses are negligible, they don't attract each other, whatever energy, it is kinetic energy, and etc. etc. All right, but practically it does not take place. They have interatomic or intermolecular attraction, they have finite size, especially when the pressure is very high, especially when temperature is very low and extremely high. On both the situations, the gas behave as real gas. That means they show some limitations. They don't obey the Charles and Boyle's law perfectly, and that is why they are called real gases. Okay. Now question is that why they behave differently. So you mean, then we mean to say that PV is equal to RT, the gas equation. This gas equation means the behavior of the variables under certain conditions is true everywhere. That means the gas is obeying Charles' law and Boyle's law is correct or not, or there any need to rectify it, correct it? Yes, it is required. So what will be that? So first thing, the pressure is P of the gas, and we know that the pressure is, there is reduced pressure small p, two terms. From where this reduced term came? Now take care of this. Now that you imagine in your in your mind that the picture that the gas pressure exerted by an ideal gas inside a chamber which is cubical inside in shape, right? So molecule going and attacking on one wall, okay, striking one wall, and there is impart of momentum. All right. So imagine there is the molecules which are away from the boundary wall. Boundary wall means wall of the container. So what happens? This molecule, the molecule, it is here. This molecule is being attracted by the molecules surrounding it. So there is attraction, force of attraction from all sides. Okay. This force of attraction among the molecule is called cohesive force, force of cohesion or cohesive force. Now this cohesive force is from all sides, thereby they cancel each other. All right. So suppose this molecule is here and number of molecules are enormous. So any molecule is surrounded by almost same number of molecules from all sides in a spherical structure. So therefore the net force experienced by this molecule by the friend molecules is equal to 0. But think of a molecule which is very close to the boundary wall, this wall. So now you see here this molecule, okay, this molecule has attraction from left hand side or upside down side because the molecules are, this is the boundary wall. So molecules are being, this molecule, particular molecule is being attracted by all the sides other than the right hand side. All right. So what will happen when this molecule will attack or will strike the wall? So this molecule is attracted, or this molecule is facing or experiencing forces from all backward directions, from the backward directions. And despite that it is striking, so we have calculated, so it is when it is striking the molecule, all right, I'm sorry, striking the wall. So the momentum imparted to the wall is actually less than it should have been because it is this molecule is being pulled, even then it has stricken the wall. All right, meaning by we calculated, how we calculated P, the number of that we calculated, we assumed it that this is imparting momentum is equal to 2 mv. All right, and number of such molecules, total number of molecules we also calculated, then we multiply it. All right, but but it has contribution, those molecules which are at the boundary on both the sides, they are, they would have given more pressure or the force, in other words, if they would not have been here, if they would have not been pulled by the neighboring molecules from left hand side in this boundary from right hand side. That means whatever pressure you are measuring, pressure exerted by gas, is not correct. Actually it should have been little more, right? So what is little more? That is the correction term. So we should have added a correction term that is equal to small p. So instead of p, there should be p plus small p. All right. Now come to this contribution of this p. So this correction term p depends on two things. Number one, number of molecules striking unit area, that means the density. More molecules, more will be pulled. All right. And the resultant inward pull of cohesion on each striking molecule. The number of molecules, if more number of molecules are total, so naturally at the boundary more number of molecules you will find, number one. Second thing, that more number of molecules are in the container, so one molecule will be, the boundary molecules will be pulled by large number of molecules. So under both the conditions, we can say that this pressure is proportional to density and density. The earlier cause is also due to density. The Further cause is also due to density. So finally, P is proportional to density square, which is equal to 1 by V square. Meaning, because density is mass is total mass is constant, so we can say that it is directly proportional to 1 by V square. So we give it as a constant A by V square. That means A is a constant which is called van der Waals A constant. All right. So now there should be correction in P with this additional term. So is it all right? So P should be replaced by P plus A by V square. Now come to correction due to volume. Now what is correction due to volume? We have assumed that the volume of the molecule is negligible. All right. But it is negligible when the gas area or volume, I'm sorry, the volume of the gas is suppose 50 liter, then only it is negligible. Suppose the volume is 1 cc, then you cannot neglect the volume, total volume due to n number of molecules. It has finite volume. So what happens? One molecule has suppose volume Vm, one molecule. So for two molecule, 2 Vm, for n molecule, for n Vm. Okay, so n Vm collectively finally give a number, and finally the effective volume is this V minus, because those molecules are already, we assume that the V is the volume of the gas, but actually it is not. The available volume is not V. Available volume is total V minus the volume already occupied by gas molecules itself. So therefore it should be subtracted. So this B term is the subtraction correction term, and it is equal to 4NVm, where Vm is the volume of one molecule, each molecule. This is also called co-volume. One year this came as the objective question, that what is this, what is Vm called? Co-volume. It is called co-volume. So finally we have van der Waals equation. In place of PV is equal to RT, we have P plus A by V square into V minus B RT. So this is van der Waals equation. We don't say van der Waals correct equation. This is van der Waals equation, or the modified or corrected equation of state. All right. So now this is corrected equation. Now what is critical constant? We know that when there is change in volume, okay, so what happens when you increase the pressure of a gas, the volume decreases. All right. So when the volume decreases, so you know that after certain limit the volume decreases in, what is the meaning of volume decrease? The interatomic or intermolecular distance is decreased. So when it is too much decreased, so it gets liquefied. All right. So vapor gets converted into liquid form. All right. And if further done, so it is solidified also. So in this process, the temperature and pressure both have effect. All right. In conversion of state, the temperature and pressure both plays a vital role. So we know that when a gas is compressed, okay, or there is change in volume at certain temperature, the volume decreases with increase in pressure. All right. But we find that there is a limit below which, so due to increase in pressure the volume decreases, and finally there is a liquefaction of the gas. Liquefaction means the gas gets converted into liquid, but this is not possible at all the situations, for which we need that the temperature of the gas must be maintained. That means, what is the meaning of saying that? If pressure is increased, the volume decreases, but it will and due to that there will be a liquefaction, or liquid, it will be converted into liquid. But this is possible under certain temperature only. You cannot apply very high pressure, extremely high pressure, when the temperature is very high. No, the basic temperature or operational temperature must be low. This temperature depends or varies from liquid to liquid or gas to gas. All right. The temperature below which the gas can be liquefied under the action of or due to application of pressure is called critical temperature, above which whatever you apply pressure, the gas cannot be liquefied. Followed what I am saying? The gas, try to listen sentence. The gas gets yes.
चलिए
Is it clear?
Yes, sir.
Yeah. Now the gas volume decreases with increase in pressure. All right. After certain times, the volume is so decreased that it liquefies into liquid, or it gets converted into liquid. But this takes place, this conversion of gaseous state to liquid state, only at certain operational temperature. There are some certain temperature below which, by application of high pressure, the gas can be liquefied, above which, despite application of any high pressure, the gas cannot be liquefied. This particular temperature is called critical temperature. That means the gas can be liquefied only below critical temperature by application of pressure, above which it cannot be. This critical temperature and this corresponding volume and pressure are called critical volume and critical pressure, and collectively they are called critical points. So critical points are critical temperature and corresponding volume and pressure. That means critical temperature, critical volume and critical pressure are collectively called critical points, and they are called critical constants, denoted by Tc, Vc and Pc. Is it clear? Every gas has their own Tc, Vc, Pc. Every gas. It is different for different gases. The Tc, critical temperature, the critical volume and critical pressures are different for different gases. Now, what is Tc? Tc of a gas is that temperature above which the gas cannot be liquefied by applying any large pressure. That is what I told. Okay. And below which only it can be liquefied. At critical point, the rate of change of pressure with volume is zero, isn't it? Because at critical point, what will happen? This is a point. This is not the curve. Suppose it is changing. So it is changing, it is changing, it is a curve. So at this point, there is no conversion. Therefore, the rate of change of pressure with volume is zero. That means the volume will not change with application of pressure. So that is why it is called critical point, and the slope becomes zero, and this point is called point of inflection. This is also an important question for objective problems. Okay, objective questions. What is point of inflection, or otherwise that uh, the the rate of change of pressure with volume becomes zero at which of the following? So critical point something 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 and point of inflection. So these are the questions. So now we oh, critical constant, critical point. So now we come to this point. So we have finally the van der Waals equation plus A by B square and into V minus V is equal to RT. So from here can we write T is equal to RT by V minus B minus A by B square, second equation. So at critical point, dP upon dV is equal to 0. All right. So what will happen? dP upon dV is equal to 0. So critical, we are taking critical point. So naturally, at this point, the temperature becomes critical temperature, volume becomes critical volume. Then finally putting the value, what we can write? We write for these conditions. In place of T, we write Tc, in place of V, we write Vc, and finally we find Vc is equal to, because here you see, this we want this Vc, Tc and Pc in terms of van der Waals constant, in terms of constant, because B and P, they are variable. R and B and A and B are van der Waals constant, which is different for different gases. These are constants, and R is already constant. We want that Vc, Tc and Pc in terms of the constant parameters. So here we find, after solving, this is the equation. So you can do it, you should do it. Vc is equal to 3b and Tc is equal to 8a by 27br and Pc is equal to a by 27b square. Don't get confused with all these. It is very simple. If you put the value, you will find it. And for final exam, university exam, this is important also. You are many times asked such questions. Now, there is a temperature which is called boil temperature. What is this boil temperature? The boil temperature is that temperature up to which the Boyle's law is valid. All right. What is Boyle's law? P is inversely proportional to V when T is constant. All right. So at boil temperature, we have found that the TB is given by, this also I have not derived, A by RB, and this temperature of inversion or inflection is 2A by RB. So from here we can say that Ti is equal to 2 TB. That means temperature of inversion, or sorry, inflection is equal to twice of the boil temperature. This is also a key or hint for numerical problem, could be asked collectively, not independently one question, but in a problem itself, this relation could be asked as for the use. Okay. Now putting the value, finally we put the value of A, B, R, etc. We get Ti is equal to 6.75 Tc. Okay. So this is one relation. Now we come to for real gases. Now all these we are discussing. The moment we introduced what? A and B, that means we are considering the gases with limitations, gases with weaknesses, and the weaknesses we have already discussed. So now come to corresponding states. So corresponding state means, suppose we have two gases, gas 1 and gas 2. So law of corresponding state called is that if two gases 1 and 2 are there, then the ratio of their actual pressure and critical pressure is equal to their actual pressure and the critical pressure. Then the similar is the situation with the gas 1, the ratio of the volume to critical volume of one gas, volume of second gas to critical volume of second gas, and critical and temperature of first gas to critical temperature of first gas to the temperature of second gas and critical temperature of second gas. If these conditions are fulfilled, then we say that these two gases are in corresponding states. This is called law of corresponding states. This is all the same. If they follow, they are called in corresponding state, and the law says that if the two states are in corresponding state, thus this situation will be fulfilled. So law and the definition, they are the same. Okay, don't get confused. So finally we have, then they are called in corresponding state. That means the ratio of their actual pressure, volume and temperature, and their critical pressure, critical volume and critical temperature have the same value. So surprisingly, all the gases have one thing very unique, that if their pressure is more, their critical pressure is also more. Okay, if their volume is more, their critical volume becomes also more, and so on and so forth. Therefore, their ratio remain constant. So van der Waals critical coefficient is that quantity. What this PV is equal to RT. So we have written PV in place of PV. We did write PC VC is equal to RTC. So finally, this whole thing is a constant, and this constant is called critical coefficient of a gas. And surprisingly, a gas whose critical temperature is more, then automatically the PC and VC are so adjusted that for all the gases it becomes equal to 8 by 3. 8 by 3. So this is for real gas. This is for real gas. So for an ideal gas, the Cc is 1. That means it should be, because PV is equal to RT simply. So PV is equal to RT means all cancels out. We have the 1. But it is not so. It is 8 by 3. So there is a great deviation. You see, in place of 1, we have 8 by 3. So it is more than double, right? So this is the relation. And the last one is for an ideal, reduced equation of a state. So P by PC, if we assume alpha, V by Vc beta, and T by Tc as gamma, then P can be expressed as alpha Pc, V as beta Vc, and T as gamma Tc. So if we substitute in place of PV T, so we substitute all these, and putting, we at the same time we have relation for PC. Okay, so time is over. Yes, I'm finishing. So we have relation for PC in terms of gas constant A and P. So if we put all these, so finally we get alpha plus 3 by beta square into 3 beta minus 1 is equal to 8 gamma. Here, what is important is that expression is in terms of alpha, beta, and gamma. No business of PVT. This alpha, beta, and gamma are made of the constants. All right. So this is why it is called reduced equation of state. Why reduced equation? Means it is the common. It is the common. It has the, if you change the PV, it is not going to change. Okay. No need of PV and T here. So this is all about. And last is when we do Joule-Thomson cooling, that means the gas passing through a porous plug. So we find that because of it is a real gas, there is interatomic attraction. So when gas passes through it, so what happens? There is suddenly expansion of gas, and adiabatic expansion, the energy is, because adiabatic condition, air is bad conductor. So energy is taken from the internal energy of the gas molecules, and therefore its temperature decreases. So that is called adiabatic cooling also. And the decrease in temperature is given by this expression delta P upon Cp 2A by RT minus B. Okay. And the rate of change of temperature, that is decrease in temperature per unit pressure in increase is given by this constant is called Joule-Thomson coefficient. Okay, mu. So this T is very important. T is, if T is operational temperature and Ti a temperature of inversion. So if the T is less than temperature of inversion, it is cooling effect. If T is equal to temperature of inversion, there is no change in temperature. And if T is greater than inversion temperature, there will be heating in place of cooling. So that is why the experiment performed with the Joule-Thomson experiment, it was performed with a large number of gases. And it was found that there was heating effect with hydrogen and helium, but with other gases there was cooling effect. So people were very perturbed at that time how it happened, why there is heating effect with hydrogen and helium. Now later on it was found that the inversion temperature of hydrogen is 195 Kelvin, which is much which is much lesser than the normal atmospheric temperature, right? Atmospheric temperature is above 0 degrees Celsius. It is much less. Helium, it is 23, even less Kelvin. So, since the working temperature is greater than inversion temperature, therefore, there is heating effect. For other gases, the working temperature, the inversion temperature is greater than the working temperature, that is the normal temperature, atmospheric or room temperature. Therefore, there is cooling effect. This is all about, in short time, I could brush off the assigned syllabus. Okay. Now, the question is problem based on kinetic theory, real gases and molecular collisions, etc. That is not possible right now. What I will suggest, I will give to Punita ma'am or the coordinator the problems along with the answers, right? Solutions. But I would suggest that you should first attempt yourself own, and when you feel any difficulty, then you take help of the solution, my solution. Okay. So students, this is all about the thermal aspect, what I could do. Okay. I hope that a little benefit you must have got out of it. Okay. If you have any problem, you are free through your coordinator. So I'm always be happy to help you to whatever possible extent. Okay, thank you very much, and thanks to the host today and Dr. Punita ma'am and other people, concerned people. Thank you very much to everyone.
Sir, thank you so much. I'm really grateful to you. It's like my dream come true. I always say everybody should get, when we talk of equal opportunity, then every student should get equal opportunity from listening to the best of all teachers from all over the country. NPTEL made this initiative at the IIT level, and I thought of this initiative at the university level, that every student, wherever he or she is, should get equal opportunity to listen to people like you who have authored books, who have got experience of several years, and best of all, who have got real clarity of of the subject that they have chosen to teach here. So thank you so much, sir. We are really grateful. And if you give any other material, then I shall keep in touch with all those students who decide to keep in touch with us. So through WhatsApp as well as email, they're most welcome to stay in touch for next 30 years or 20, or as long as I live. And I'll be free to help them always. So sir, if you pass on, I shall pass on to them. Yes. Dr. Savita has started doing some numericals. She did some numericals on kinetic theory and transport phenomena last day. 1 hour of numericals she chose from Net, Gate, Jest and Jam. And few she did with the students in her 1 hour lecture. So we are trying whatever we can fit till 11th October, we are fitting. However, the long series of thermal is almost coming to an end with your teaching. We will have just 1 or 2 more hours of numericals with Savita, Dr. Savita. So thank you so much, sir. Once again, we are really grateful. I personally shall remain always grateful. Thank you so much, sir.
I'll send the material as many of the students wanted. I'll send you, okay, and thereafter you take care of it.
Yes,
Thank
sir.
you
Yes,
very
sir.
much.
Sure.
Thanks all.
Thank you so much, sir. Thank you so much.